Hello, good morning, good afternoon, and good evening to everybody who has joined us from around the web for a special webinar broadcast brought to you by Park Systems. We're a leading manufacturer of atomic force microscopy and emerging nanoscale microscopy technologies. My name is Gerald Pasquale. I'm here with the U.S. Office's technical marketing team, and today we have again Professor Rigoberto Advincula of Case Western Reserve University. And today we will be looking at 3D printing and advanced manufacturing, part of our 101 series, a perspective dealing with the fundamentals of the science behind various fields, including, like you see here, 3D printing and advanced or additive manufacturing. So if this is your first webinar series with us, please note that your mics are muted by default. That's by design. We wish to give Professor Advincula a smooth, uninterrupted speaking experience. But if any questions at all come up that you want to relay to us, please use the chat or the questions module in the control panel that popped up when you joined the session. And what we'll be doing, we will be taking those questions and answering them sequentially at the tail end of today's session after the professor has finished his talk. With that said, this session is being recorded, so if you need to show this to someone who wasn't able to make it today, a colleague or a student perhaps, these will eventually make their way onto both parkafm.com, our website, as well as the Park Systems YouTube channel as well. So just search Park Systems on YouTube, and you will see not only this webinar recording, but also recordings of other sessions given by Professor Advincula, as well as our other speakers as well. So with that out of the way, let me go ahead and turn things on over to Professor Advincula. Professor?
Okay, well, thank you, Gerald. Again, good morning, good afternoon, good evening to all of you, listening audience. And at the end of this session, since this is a live webinar, you will have the opportunity to ask questions and we will answer them sequentially. So first, I'd like to describe broadly the topic. In this hour that we will have the opportunity to present 3D printing, I will be discussing some of the basics of 3D printing, and then focusing on materials, polymer materials specifically, and the use of nanocomposites. In fact, I will try to give you a perspective on some of the unique opportunities and challenges of 3D printing together with its application for advanced manufacturing. I purposely interpose advanced and additive manufacturing because additive manufacturing has enabled advanced manufacturing with different supply chain mobility dynamics, and additive manufacturing is very specific for the type of process to additively produce different types of design and objects versus subtractive manufacturing, which involves removal of parts or components of a material. So let me introduce Case Western Reserve University. I'm a full professor at Case Western Reserve University, Department of Macromolecular Science Engineering, and we have lots of culture, lots of opportunities to do lake activities, sports, and Cleveland also is home to a great medical clinic called the Cleveland Clinic. We do work related to chemistry, polymer science, different types of processing methods of polymer materials. This is our building at the Macromolecular Science Engineering building, and I'm located at the 5th floor. Here I'm showing you a new facility institute that is available and open to the public as well, called ThinkBox. It's an institute that allows us to collaborate and innovate. In fact, in 3 weeks, we will have an international conference on makerspace, which is basically an education arm and entrepreneurship focus on 3D printing and additive manufacturing for a lot of institutions. So here in this institute, we have many tools for 3D printing and even subtractive manufacturing and rapid prototyping or design. As you can see here, we have a number of big instruments from Stratasys and 3D Systems as well. In fact, ThinkBox really is a rapid prototyping facility that is very much used by our students to design and use for their own projects and even for their own startup companies. Now, other than 3D printing, we have lots of activities involving coatings, but one unique center that has been funded for the last 10 years is this facility called CLIPS, or Center for Layer Polymeric Systems, that has allowed us to explore multi-layer processing, packaging, and in particular, I led a group or platform focused on development of these films for a number of applications in drug delivery, packaging, patterning, particle technologies, as well as bio-related applications. So with that introduction, let me then focus on 3D printing for the rest of the time. So last year, I was a speaker at the World Economic Forum, the Future of Materials Council, and this was held in Dubai last November. In fact, I will be going back there in November as being a member of the Future of Advanced Materials Council. So I gave a talk on and an overview of 3D printing, its perspective in terms of value chain adding, as well as remote fabrication and manufacturing, and bio-inspiration. So a good question is, what are the advances in 3D printing and additive manufacturing that will make it useful for the 21st century? Let's start with machines. Machines are definitely available. You can buy your own 3D printer for as little as $100, $150, and that's good enough for a lot of hobby type of 3D printing time. On the other hand, big build volume 3D printers are being explored for actual manufacturing and limited production for parts replacement. The science is still on. There's a lot of work being done on exploring various strategies and mechanisms for 3D printing, including the use of cross-linking, photopolymerization. And of course, when I talk about 3D printing, I'm not just talking about polymers, but the various material classes, including the big three, which is polymers, metals, and ceramics, are being explored in the 3D printing value chain. Now, one thing that I like about 3D printing is inspiration. Because of our digital age, we are able, for example, to take the design of that's found in nature and convert it into different types of not only beautiful but functional design aspects that can be used to strengthen materials, to strengthen or produce different design concepts and mimic nature. And when I talk about inspiration of nature, of course, it can be based on both mammalian and as well as the plant kingdom. However, my first introduction with 3D printing actually started even 20 years ago when I heard about stereolithography. SLA actually is a newer term, but in the past, stereolithography and two-photon polymerization has been used to produce interesting objects in the microscale. As shown here, the effective use of light and a resin material that includes monomers and initiators and cross-linkers allow light to be directed stereolithographically to produce objects in the micron to centimeter scale. And this is all digitally processed based on movement, let's say, of micro lenses or elements of DLP, or digital light projection. Be that as it may, stereolithography is only one type of 3D printing that is out there when applied to polymers. Another focus I would like to point out is on biomedical applications. So there's a lot of interest, in fact, commercial interest on using 3D printing for prosthesis, for bone replacement, for dental application. Here, what's interesting is a lot of bone replacement applications which can be done either by ceramic or even high-strength polymer materials such as PEK. Is a very good alternative towards alloys like titanium alloys. So in fact, 3D printing allows us to make design as complicated or as varying in density as shown here, which actually can be used to change the density of bone. Bone density is very different from different parts of the body, and especially for craniomaxillofacial surgery, a very much bone replacement or osseointegration or resorbable polymers, which eventually is replaced by bone, is a hot topic of research in the biomedical field. Along with bone research, a lot of interest on 3D printing actually goes towards bioprinting or tissue engineering, where scaffolds can be 3D printed based on hydrogel that's extruded in a thixotropic viscous form to become host towards cell growth or tissue engineering for grafting or production of synthetic organs. Now, closer to manufacturing, there's a lot of interest on 3D printing for automotive and aerospace lightweighting. Automotive lightweighting means you replace parts, body parts made of metal or aluminum or even engine parts, if possible, with lightweight material that can include high-performance polymers like PEEK or even other types of metal alloys. Actually, what's interesting with 3D printing is you are able to revive old design. For example, this classic spider car, and by the way, this image is acknowledging the 3D printing demonstration of cars from Oak Ridge National Laboratory, has shown that 3D printing can go towards limited production or manufacturing that can be as big as cars or wing parts or even parts that are useful for wind turbines. So big build volume is actually present right now, and there are companies like Cincinnati Machines that are able to make big build volume machines for 3D printing plastics and other composites. In fact, there's a lot of interest on 3D printing for construction or 3D printing of different structures that may even eventually be useful for space or habitability or survivability in the moon. And so space advanced or 3D manufacturing is actually being explored by NASA. Interestingly, a category of 3D printing, which I would classify as art, has been done and has been used to create AI or artificial intelligence to make synthetic or new paintings. So let me take the case of Rembrandt. Rembrandt is a master, Dutch master, that is very popular during his time, but certainly a very rare or very valued collection in any museum. He produced hundreds of paintings, and those paintings do exist. And a project that was made in collaboration with Microsoft and ING Barry digitized or took all the metrics of his famous paintings, both famous and other rare collections. And using artificial intelligence, a question was asked: if Rembrandt were alive today, what would his painting look like? So with the combination of AI and the use of 3D printing, so this is classified as 3D printing because in order to get the excuse me, various shades, color contrast, and light, 3D printing was used to make layers and layers of color and paint to come up with a Rembrandt product. So what they did is they then created a new Rembrandt painting digitally. So they digitally 3D printed this painting, and this is it. This is a new Rembrandt. If Rembrandt were alive today, this was a composite, if not a revived painting by Rembrandt that was produced by 3D printing. So in all these initial examples I've shown you, what this tells us is that 3D printing has many aspects, uses not only for manufacturing, but also for design and introducing complexity. So this graph shows that compared to standard design or manufacturing, 3D printing allows for more complex geometries and designs. And as you can see here, the cost is not too different from a standard design, except that when you increase the amount of material or object that is manufactured, in a standard design or standard manufacturing, the cost actually goes down, whereas in additive manufacturing, the cost remain the same. Another aspect that can be compared with traditional and advanced manufacturing, such as 3D printing or additive manufacturing, is that the lot size for traditional manufacturing can be high, from cutting to casting or molding. However, for additive manufacturing, the lot size is small. In other words, additive manufacturing is still limited towards limited production. So there is actually a manufacturing gap that needs to be solved in order to take additive manufacturing more mainstream. That is, how can you increase the throughput of 3D manufactured parts or objects? So let's start by looking at some basic 3D printing processes based on these acronyms. FDM or FFF can be called the most prevalent type of 3D printing. That is plastics 3D printing, more commonly associated with some of the inexpensive printers. So FDM stands for fused deposition modeling. FFF stands for freeform fabrication. The sample based on photolithography is SLA, or stereolithography apparatus, or sometimes called solid freeform fabrication. Printing based on powders are called selective laser sintering. And one that involves other methods such as plaster or resin have specialized names. So as you can see here, there's a lot of interest on automotive application, consumer products, biomedical, aerospace. And the biggest advantage yet of 3D printing is on-demand, limited production of high performance, value, or unique design or complicated geometries that results in high value adding. Now, there are problems, and I want to emphasize some of this in terms not only of the amount of object produced, but on the material itself. Take the case of FDM, fused deposition modeling. So in fused deposition modeling, a thermoplastic is actually heated, a filament of thermoplastic is heated from the head and then melt delivered or extruded on a nozzle. That nozzle then moves based on the programming of the apparatus to move in one direction and fill up layer by layer, okay, a build platform, which eventually moves to allow for the build-up of the object. But the big problem here is this type of printing produces a lot of failure based on the quenching of small layers or small printed material that is exposed to air. So eventually you build up an object, but compared to a monolith object, which is produced by injection molding or thermoforming, the failure mechanism stems from all these quench lines or anisotropic quench lines that are produced by the printing process. But nevertheless, this process is predominantly used for 3D printing plastics such as ABS, polycarbonate, polylactic acid, high-density polyethylene, etc. Okay. Now, our objective in our group, at Vincular Research Group, is to improve on the materials that can be 3D printed, not only with FDM, but including SLS, SLA, in order to increase its thermomechanical properties and chemical resistance. And we do this by utilizing nanocomposites, chemical additives, blends, and copolymers. Now let's take the second type of printing. And this one is based on sintering or SLS. SLS involves the use of powders where a laser is scanned or moved that results in sintering or fusion or melting of these powders to create an object. Each time a new or fresh layer of powder is added such that the layer is built up and the platform is moved to accommodate for that additional layer. So at the end of the printing, you have an object that is actually embedded on a powder. And SLS has been used to make objects based on polymers such as polyacrylamide, PEEK, polystyrene, or elastomers, and even use it for direct metal laser sintering. And by the way, most metals are printed this way or by sintering process. So this example, which I showed earlier, is based on photolithography. So photolithography means that you use light to enable polymerization or photopolymerization of a resin composition that contains a monomer, a dimer, or a cross-linker, and diluent monomer, or additional additives that enable nanocomposites or better 3D printing properties. So in an experiment, in a apparatus that allows light to be directed precisely at a specific plane, directed, let's say, by a micro lens or in a digital light processing apparatus. So a good example would be a projector, an LCD projector. Photopolymerization takes place selectively until you form an object out of that resin, and then you can rinse off the extra resin to produce the final object. So photopolymerization, as shown here, is eventually build-up of that cross-link or photo-cross-link material into various shapes and sizes all the way to the micron level, such that this is basically chemistry that was borrowed from the coatings industry. So these are representative monomers or cross-linkers that have been used for photopolymerization or SLA and DLP. Of course, there's a difference between SLA and DLP in that the combination of light as well as control on the amount of free radical initiation and polymerization taking place can be projected from the top or from the bottom. And I've seen instruments or machines these days that are as cheap as $600 and basically uses a LCD projector to do a photopolymerization. Nevertheless, to distinguish this from the first two that I described, this actually involves chemistry, not just melting, but polymerization itself of the corresponding monomer and initiators. Okay, so going towards the different materials that can be 3D printed and their applications. Okay, so I apologize for that. Looks like we have a PowerPoint presentation that had to quit, but let's start. Okay, so whereas we can be talking about metals, ceramics, hybrid materials that can be printed, today I will simply focus on polymer materials. So polymer materials, or sometimes we just call them plastic, are essentially high molecular weight molecules that can be derived from petroleum feedstocks or bio-based feedstocks. And they're both good and bad, but one cannot argue that modern society today is very much dependent on polymers. Polymers can be classified as high commodity polymers that are low cost, like polypropylene or polyethylene, or high performance polymers with ultra polymers that can essentially replace some of the function of metals. And as you can see in this pyramid, the base of this pyramid constitutes your commodity polymers, and majority of what is 3D printed out there are essentially commodity plastics or thermoplastic. What is harder to 3D print are the high performance polymers like PEEK, PAEK, or ULTEM. And this type of polymers require higher melting temperatures. On the other hand, thermoplastics is just one subset of polymers. Polymers can constitute thermoplastics, elastomers, and thermosets. Thermosets are essentially cross-linking of material systems such as epoxy, cyanate ester, polyimide, or phenolic esters, phenolic-based resins. On the other hand, high-performance polymers like PEEK or even PPS are essentially thermoplastics with a high melting point and can be crystalline or amorphous. As you can see here, the cost almost tracks the increase in normalized tensile strength. So 3D printing means that in order to make it useful for a variety of applications in the, let's say, automotive, parts, tooling industry, or aircraft industry, they have to reach the performance of high tensile strength, such as PEEK. Ordinary plastics like polyethylene, polypropylene, ABS, or PLA have limitations in that they cannot be used for higher temperature or high thermomechanical applications. But let us review some of the traditional fabrication methods. So extrusion, injection molding, blown film molding are ways that plastics can be processed into objects or pipes or different types of consumer goods. And the advantage is that the die or the a mold can be produced, and that will allow production at a high throughput. And also, this type of polymer production are based on monoliths. They're not made layer by layer, but they're simply molded, injection, and the object is derived from the melt polymer. Here's a picture of injection molding, and you can see in a molding fabrication, you have a mold which can be based on aluminum, and the melt resin is added to that mold, and you produce your object. Yet another traditional method of manufacturing is based on thermoforming, where the application of pressure, vacuum, or mechanical pressing of a sheet produces a finished part. So one would say that these traditional methods are not under threat with 3D printing, simply because these traditional fabrication methods are the viable are the only viable solution for high throughput manufacturing and production based on existing tooling that's out there. The question is, when will 3D printing replace traditional manufacturing? Or another question is, when do I use 3D printing versus traditional manufacturing? Revisiting some of the common plastics or polymer out there that is 3D printed. This can be based on ABS, PLA, or polycarbonate. These are commodity plastics. And as I mentioned, for high performance, usually these common commodity plastics are not enough. But 3D printing has gone into lengths of producing 3D printed parts that can be based on gold, metals, ceramics, even chocolate or food. In other words, 3D printing is not limited to plastics, but there's a chance to introduce more chemistry, more viscosity-driven printing, more dissolution methods, more curing methods, along with 3D printing. Hence, this table is quite telling in that a lot of interest on polymeric materials, yet there's also a bigger community that is focused on metals or metallic materials that can be 3D printed versus cast or molded systems. So high performance materials such as titanium are, for example, advantageous because of their non-corrosion properties, or even noble metals such as gold and platinum for the electronics industry. On the other hand, ceramic materials and refractory materials such as alumina, zirconia, silicon carbide are of high interest in various industries and have complementary properties because of their hardness and insulation. So one can say that 3D printing has a lot of promise in various applications and industries, and there are many choices for materials, but the most predominant 3D printed materials out there are still based on polymers. Okay, so let's review here some of the potential applications of 3D printing. So the promise of additive manufacturing can be found in the aerospace industry, the automotive industry, biomedical community, electronics industry, marine, oil and gas industries, and of course, different consumer design and fashion industry. In fact, additive manufacturing can now be combined with traditional methods of manufacturing, including subtractive manufacturing or casting or molding to come up with new uses. Okay, and so a good question is, in terms of entry to industry, what would be a good entry point to replacing casting or molding or injection molding by 3D printing? Or where can 3D printing be utilized to improve traditional processes or cut production time or enable, let's say, the preparation of molds in a short amount and less expensive project? Anyway, possible applications, as you can see here, can involve replacement of design or combination of materials and design. For example, the need for heat dissipation or rapid mixing or exposure towards chemicals or corrosive environments, or simply lightweighting and reinforcement. As shown here, 3D printing of metals or ceramics have much promise in terms of replacement of traditional molded or casted parts, And of course, the advantage of 3D printing is the ability to make complex design, which cannot be approached towards using traditional methods of casting or molding. In precision engineering, there's interest, of course, towards more refined parts, not only complex parts, but high resolution parts. One of the problems, for example, with metals and 3D printing of metals is that they are not the same in terms of their thermomechanical properties as, let's say, alloyed steel that has been heat treated or produced using optimized methods of annealing. Of course, the electronics industry is another ripe area for 3D printing applications, not only on the PCB board, but different types of vertical design geometries and the introduction of metals, insulation, and heat sinks or heat controlled design and materials. I showed this design to you earlier. One question here is, what was actually 3D printed in this car? What type of scale and throughput? What parts are long-lasting and short? In other words, do you expect this car to last for months or years? Or in a road condition, what will be exposed in terms of thermomechanical properties? On the other hand, as I mentioned, as you can see in this revived design, 3D printing is good for reviving or manufacturing parts that no longer exist, or looking at design, new design concepts that can be introduced together with old design concepts. Or take the case of this lightweight car or hybrid car system that can be used to have high mileage or rather low mileage, high speed combination that can be introduced rapidly using 3D printing. Or in the case of car parts or metals or replacement of engine parts, how can you produce lightweight materials that can withstand, let's say, combustion? Or one interesting question is that, is it possible to make a plastic combustion engine that can replace parts of a metal engine? The answer to some of this involves the use of carbon composites or ceramics, or in this case, carbon fiber composites involve the introduction of carbon fiber together with the polymer resin to produce lightweight parts. In the case of the automotive industry, very important, not only for lightweighting, but for high-strength materials. So there's a big move for applications in the automotive industry, both inside and outside. Another example that warrants the use of 3D printing would be the oil and gas industry, because of the need for repair and replacement or even new design that exposes some of these, let's say, packers, rubbers, or screens or different alloys under high pressure or high temperature condition. Okay. Prototypes or real parts, that's a good question to ask whenever you prepare materials with new design and applications that eventually will go to high performance materials. So for example, replacement of metals with high performance polymers like PEEK has gained a lot of interest, but the problem is PEEK materials are not easy to 3D print because they require a high melting temperature oven. Or in the case of rapid prototyping or production, can you have machines that produce in an additive manner lots of parts or high build volumes? So anyway, I'm ready to conclude at this point. What I have shown you for the last 45 minutes or so are aspects, perspectives, and a good survey of materials, specifically polymer materials, and the different type of 3D printing options we have for advanced manufacturing. So hopefully this afternoon this talk has given you insight and inspired you to learn more about 3D printing and its uses and ability to change how we do things in the 21st century. So with that, I'd like to end the talk, and I'll be happy to answer any questions you may have.
All right. Thank you very much, Professor, for the very thorough look at 3D printing and additive manufacturing techniques as they are today. As the professor mentioned, we are now moving on to Q&A, and there is already a question here in the pipe, but go ahead and use the questions module, the chat section of the control panel. Go ahead and type in your questions. We will continue answering them for the next couple of minutes here on online. And if you happen to have any questions afterwards, if you could put up the first slide of your presentation again, Professor, with your email address. He is reachable through email. And if you have any questions about Park, you can also send us an email at inquiry@parkafm.com. I'll leave that email address in the chat module, or you can just visit our website at parkafm.com. So our first question for you, Professor, is first, thanks for the very interesting talk. How fast is making car parts by 3D printing? How fast are these methods versus the standard ways of making them?
Yeah, good question, and that was a good first question. The answer is slow. 3D printing is still a slow process, especially for techniques that involve high build objects, high build volume objects. We can be talking here about anywhere from minutes to hours to even days to complete. But the advantage is when you're trying to do prototyping, when you want to get the object, you actually do it faster because sometimes prototyping involves submitting a sample to a manufacturing and to a laboratory or a tooling shop where they have to apply milling or subtractive CNC milling in order to produce the part. So in that case, 3D printing has an advantage in speed in terms of prototypes. But at any rate, 3D printing cannot compete with high throughput manufacturing methods such as injection molding, blow-fin molding, which can produce parts at a relatively inexpensive, especially with high volume and in a fast manner.
All right, thank you very much. Looks like we're still waiting for maybe one or two more questions to come into the pipeline. As for something that I was personally curious in, Professor Advincula, is I remember maybe not too long ago, around 3 years ago, maybe 5 or so, we started to get a lot of movers and shakers in getting 3D printers into households, into I believe companies with like Maker, I believe. Now I'm wondering that seems to have cooled off a little bit. I'm not really seeing 3D printing as much in, let's say, mass media stories about the technology. Do you think things have stalled a little bit in the consumer space for using 3D printing technology? Do you have any thoughts about how it could be revived again, could be hot again?
Well, I would say one of the things that I see as a parallel with the 3D printing environment is how the IBM PC or the clone was democratized eventually with the development of cheaper versions. I mean, not knockout parts, but faster processors, things like that. Actually, 3D printing has been more accessible more than ever. Has now been accessible more than ever to many households and families because it's relatively inexpensive to buy those small 3D printers. However, the buzz is somewhat lying low these days simply because the market needs to catch up. And I'm not sure about how the stocks are for companies like 3D Systems or Stratasys these days, and I've been hearing that they're not doing so well. It could be that the 3D printing has to go to the next phase with addressing some of the limitations in materials, limitations in the speed, the throughput, and the type of machines that can be used to produce actual parts. So in that case, 3D printing has to address some very specific market challenges as well in replacing traditional methods or improving its value chain in industries like the automotive industry, the aerospace industry, or the tooling industry. So there has to come to a point that those industries that are existing will be challenged. Will be challenged because of technological and materials development in the 3D printing industry.
All right, thank you for the insight, Professor. Let's see. We have another question here from the audience. Let's see. It says, there are certain standards for traditional manufacturing methods, such as ASTM. However, are there any existing regulatory standards that you are aware of when it comes to 3D printed objects, especially in the aspects of post-processing and testing?
Very good question. There are committees that are being formed out there to specifically develop standards for the 3D printing industry, not only in dimensionality, performance, but also there, of course, a lot of them has to do with thermomechanical properties. But as far as what is acceptable for industry or what is needed by industry, it still is the biggest question. How will these 3D printed parts actually perform? Or what is the industry demanding in terms of their performance or ability to replace traditionally manufactured parts? So in that case, this 3D printed materials has to withstand or has to hold up to existing standards, whether it's ASTM or ISO or ISME or even API or SSPC. What prevents? The bigger question is what prevents 3D printed materials from passing or meeting some of those standards? Okay. In other words, it has to be market driven. 3D printing should not be treated any special when it comes to their actual usage. If they are to replace, if they are to carve out a market from the existing industry, they have to meet the standards by which the current industry is playing.
All right, and here's a question about how this topic relates to Case Western Reserve. One person in the audience is asking, are there any courses or any kinds of degrees from Case that would help in this sector?
Good question. I think one is a good course on materials, whether it's polymer, metals, or ceramic. And then if you want to get into 3D printing, the best way is to get into a research lab that does a lot of 3D printing, which is one of us. Ours is one of those labs that do a lot of 3D printing. Now, as far as formal coursework is concerned, I'm actually in the process of developing course modules, special topics related to 3D printing. In fact, one of the things that I regularly do is to hold workshops on various topics, including 3D printing. So it's a good question. In fact, this November in Houston, we will be doing a workshop on polymers and 3D printing. So as far as CASE is concerned, I hope many of my colleagues together with me will develop more coursework or more workshop activities related to 3D printing.
And would it be safe to assume, Professor, that information about that workshop would be available at either your website or somewhere online?
I would suggest they email me for specifics. My email is rca41@case.edu, which is on the screen right now. And I'll be happy to furnish you more details regarding the workshop and future offerings.
Sounds great. We have a pair of questions here in the pipe. The first one reads, what future can you see in 3D printing as an additive manufacturing technology in terms of viability and becoming mainstream in mass production industries?
Yeah, again, these are very good questions. So looking at and surveying what's out there, and I've been to many meetings, including Rapid, visited several companies, interacted with my colleagues at national labs. The biggest challenge really is if 3D printing were to compete with traditional manufacturing, it has to highlight several things. One, 3D printing has an advantage in complexity and rapid prototyping. Second, it has the ability for limited production of high value, high performance parts, or the ability to produce using different materials. Third, its ability to combine rapidly digital design, scanning, inspiration from nature into new design and functional aspects. Having said those, some of the challenges that I see going forward is addressing the materials needs. It simply is a fact that a 3D printed object is not the same as a traditionally casted, molded, fabricated object because of the failure modes that are introduced during the printing itself. That is, it essentially is, instead of a monolith fabrication, 3D printed materials are produced by lines or additively by layers. And each time you layer a production, you are producing failure or quenching points. So materials is a big challenge, or having the right combination of materials and processing is a big challenge that needs to be overcome in order to be an actual replacement industry. Another is, of course, as earlier mentioned, standards. Industry is reluctant to use new materials or new production methods if the material or the production method is not accepted by the market or by their peers in industry. Hence, the development of standards is going to be an important way to level or at least address the communication of protocol between companies and the acceptability of 3D printed parts. Now, the future is actually bright, and despite these limitations, the future is bright. One of the things that I see with 3D printing is supply chain dynamics or block value chain. Imagine being able to produce on site versus transporting the material on one site, or what is the case in terms of repair and replacement. Let's say in the military, there's actually a lot of military hardware out there that is not being used simply because parts do not exist, or repair of different machines or vehicles or even aircraft that are lacking parts simply because they were produced 20, 30, 40 years ago, and those parts no longer exist or cannot be obtained from um, other junkyards. Okay, so 3D printing offers the viability or solution for producing those new parts or producing limited parts that will enable the return of function and viability of machines, aircraft, car, military, or even as a national need in maintaining facilities out there. So the future is bright for 3D printing, despite some of the limitations and maybe the market needs that needs to be addressed in these coming years.
And it's actually funny that you closed that response with the idea that 3D printing can be used to replace obsolete parts, because actually just a couple of weeks ago I did just that. I actually printed out a couple of parts that I could no longer source for a couple of old film cameras that I've been trying to repair, and they've worked pretty well.
Excellent.
So
Excellent.
yeah, that's some personal experience there, that 3D printing is definitely exciting and it works. So we have a couple of minutes left here in the hour that we have scheduled. So if you have any questions that have not been sent in already, please send them in to the professor via email. We'll answer the last two questions we received. His email address is again here on the screen, rca41@case.edu. And if you have any questions for Park Systems about any of the tools or technologies we provide to help characterize, for example, some of the materials that go into 3D printing, please visit us at parkafm.com. So with the few minutes we have left in the hour, we have two more, the last two questions for today. The first one is, Professor, how is the academic community aligning itself towards preparing students to 3D printing careers?
Yes. Unfortunately, most academics are not actively yet, or still figuring out how to place 3D printing, whether it's the realm of materials engineering, chemical engineering, and certainly polymer science and engineering. What's a good starting point? At any case, 3D printing would most likely be housed in an engineering discipline. However, there's a lot of 3D printing going on in the biomedical field, bioprinting, hydrogel printing. Even in most science or colleges, chemists, okay, are very interested in 3D printable materials or materials chemists. So it will only grow. There are a couple of professional organizations, including the American Chemical Society, the Materials Research Society, APS, Applied Physics Society, IEEE, that have been doing dedicated sessions on 3D printing. So my answer is that it's only going to grow, and hopefully here at CASE, we're among some of the pioneers in 3D printing in academia.
Very good. And our final question for today's session is, do you think there comes a time when it will be possible to create an object by using 3D printing techniques, but on a molecular or atomic level?
Good question. Let's start with the nanometer level. The nanometer level or nanostructuring is actually being done or has been done. And we actually started many years ago on a technique called electron nanopatterning. So the use of a AFM, atomic force microscopy, STM, scanning tunneling microscopy, are key towards those type of fabrication methods on additive deposition of matter or materials. Of course, this can be complemented with lithography. Uh, Photolithography, electron beam lithography are methods by which patterns or objects can be created, but this involves removal of a material or use of electron beams or electrons to do chemical conversion. So the answer is in the nanometer level, yes, it's very much in that direction. Atomic level, perhaps again with the use of high vacuum STM, it's possible to move atoms, it's possible to stack atoms, and it's possible to 3D print atoms.
Thank you very much, Professor. And Andrew, to the member of the audience who asked that question, if you're curious, yes, we have done webinars that have been recorded and published online on electro-nano patterning by AFM from Professor Advincula that we did earlier, and also on nanostructured materials as well. So feel free to check those out. It seems like it would be right up your alley. So with that, we have exhausted all questions as well as our scheduled time for today. On behalf of Park Systems, thank you very much for attending and taking times out of your busy schedules to join us. And please keep an eye out in the future for webinars from both ourselves, from Professor Advincula. We typically do webinars monthly, usually 1 or 2 a month. And we hope to see you at a future talk. Professor, do you have any closing thoughts for today?
Well, again, I'd like to thank the audience. I'd, of course, like to thank you, Gerald, for hosting us. And until our next time, keep busy and good luck on your endeavors.
Thank you, everybody. We'll see you again soon.